Okay. All right. In continuation of what I did last time, which I so uneloquently attempted to show what Bessel was doing, briefly go over it again. We had a oops, wrong button. Basic equation like this. Just a second. Which others before, but Bessel gets the credit for finding a solution to this type of differential equation. So, in the handout that I just turned out, goes through the process of finding the coefficients for the solutions. And so we started with a series at this point and said that the coefficients A1, A2, and so forth have to be solved. And when he gets done, it'll look something like, let's see, where is it? About there, so that each individual A coefficient can be calculated. And again, when you get done, you have this basic equation right here, which you'd see a lot of times where they're just similar versions of each other, so you might see it in books in either form. Okay. So one of the first things to be doing is, let's see, to solve for well, a solution to this equation. And so one of the things that was done, we determined that y would be in this infinite power series right here. And so we'll work with that value of y to solve this form of this equation. So now we have a whole lot of lowercase a coefficients to work with. So the first thing to do is to differentiate y, and so we would have the infinite power series here, the first differential with respect to z, done this way, but then we put divided by z also, so that this term right in this position will fit right there. Then we take the second differential of y in this series, and it expands like that. And now we'll place each of those individual components back into this equation. All right, to make life a little easier, what I did at this point in the handout, I did those in Maple. Okay. And in this first series, this will be where n equals 0. So I set up the differential equation, or excuse me, the power series. Now, even though I stopped it here at z is to the fourth, it truly is a series, but I'm just showing it as a fourth order polynomial equation at that point. And when you take this term, what I called is dy divided by z. Okay, so that's the y equation, first derivative, and then divided by z, and that expands right here. Then the next command took the second derivative. Okay, so I did the differential of y, second derivative, expanded it, sorted it, factored it, and did a lot of fun things with Maple on there and got it into this form. Here. Mm-hmm. Okay. All right, then those components, each of these components, the y, the dy divided by z, and the second derivative of y, are then brought back together into that equation, just like this, where dy, or the second derivative, plus dy divided by x, and so forth. Now, in this condition, I left the end term or portion in there, even though for this one it's n equals 0. Okay, because I'm going to use it in all of the versions. So at this point, n would be 0. The equation is then expanded and sorted in powers of z. So we have all of the different terms. I don't know if you can see it very well or not. Okay, so we have quite a few coefficients to deal with, and again, remember, this is a infinite series, at which point I stopped as a fourth order. Now, the original differential equation was equal to 0, so right here equals 0. So if that's the case, each of the coefficients of the like terms have to also vanish. So what I did was I have the z to minus 2 term, and that's the same as these two are this one right here. Yeah, I guess that's it. Okay, so we have a minus 2z. And then we have a z to the minus 1, or 1 over z, and then z0, z to the plus 1 factor, and then z squared. So I took each of the coefficients, brought them out, and set them equal to 0, because each of those must collectively equal 0. At that point, then I factored them, and it comes out looking like this. So the 1 over z squared term has this condition, 1 over z term has these coefficients, and so forth up to z squared has these coefficients. Then I solved for each of these equations. The first one I solved for a2 in a form of as a function of a0. a3 is a function of a1, and the last one, a4, is a function of a0. Okay, a couple of interesting things that happen here. Looking back on this first one, that two conditions could be that either a0 equals 0 or mu equals 0. Okay, and you can't decide at this point, so we'll come back to that. the second one, either A1 could be 0, or mu might, or excuse me, if mu is not equal to -1, then A1 must be equal to 0. But again, we still don't know what mu is, so we'll come back to that. But we'll just press on with these. And we put them all together, and we have back to y is equal to this, which is each of these terms, each of these coefficients were placed back into the original power series. So we had the A0, the A1, A2, and so forth are the different coefficients for the various powers of z. Now I'm showing here just the first three terms. Of course, there's an A0z to the sixth, A0z to the eighth, and so on, going on out for infinite. But I'm just showing the first three. Okay, but these are all, in this case, if A0 were equal to 0, then y is defined as 0, and that obviously won't be of any use to us. Now we take that information back up here, we say, well, if A0 was 0, then that's no good. So what we have to do is say mu is equal to 0. Now at this point, remember that A1 had to be 0 if mu was not equal to -1. So in this case, mu isn't equal to -1. So therefore, A1 has to be equal to 0. Okay. Now if A1 is equal to 0, an interesting thing happened with all of the odd function or odd coefficients is they can all be put in as a function of A1. So what happens is all the odd coefficients end up being 0. So we're left with just the even functions, which are all function of A0. So when I put them back in the infinite series in this case, that's why you only see the A0 values and you only see the even number exponents. So what we'll end up with in this case is a coefficient A0 in front of with z to the mu power, and in this case again we've already decided or found that mu is equal to 0. So in this case we'll put mu equal to 0 through here. Z to the 0 would be 1, and so we'd have A0 times 1 minus z squared over 2 squared plus z to the 4th over 2 squared times 4 squared minus, and continuation. So we have a infinite series for the value of y with a coefficient A0. All right. I went through the same thing for n equals 1. So you just put in n equals 1 in here and go through the whole process again. And when we get done, we have these coefficients. Okay, with the same reasoning we had before, at this point you could have A0 equal to 0, or mu could be equal to 1, or mu could be equal to minus 1. All right. When we get down to the bottom, just like before, we get down here and we find that, again, if A0 was 0, we don't have a very good equation, so that's not going to be a choice. But another thing is you'll have occasionally a term in the denominator where mu plus 1 is down there, and if mu was minus 1, then that would be a 0, and then that term would go to infinity, and so we haven't found a solution. So we'll come back up here and say, well, a equals 0 is not a choice, and mu equals minus 1 is not a choice, so we're left with mu has to be equal to 1. On the second term, we find that in this case, if mu is equal to 1, then A1 must be equal to 0. Okay, again, if A1 is equal to 0, all the odd terms of A are again in a version of A1, so they are also all equal to 0. So we're left with just the even values, so A2, A4, A6, and so on. So we end up with this final series, and that would be for n equals, for n equals 2, which is the same as, I'm sorry, n equals 1 I'm working on, and mu is equal to 1. So you put in the values of mu is 1 through all of this, bring A0 in the front, and in this case, we set A0 equal to 1/2. All right, I'll get back to that later. All right. Now here's n equals 2. Again, you follow through the same thing we were doing for n equals 0 and n equals 1, and you go through the process, and you come to this condition. And again, we have a choice of A0 could be equal to 0, or mu could be equal to minus 2, or equal to plus 2. And again, for the same reasoning, down here, A0 better not be equal to 0. So, excuse me, one other one is there's a term here where if mu was equal to minus 2, this would go to infinity and it wouldn't solve the equation. So we've said A cannot be equal to 0, and mu can't be equal to minus 2, so mu has to be equal to 2. Looking at the second one, if mu is equal to 2, then A1 has to be equal to 0. And just like before, it knocks out all of the odd values for A, because again, they're all in functions of A1. So we end up with an infinite series again, just like this, where we'd have z to the mu power times A naught, and then times 1 minus, and then each of the terms. And again, this would be a power series, or a series, an infinite series. And in this case, okay, we've already set mu equals 2, and I'm going to arbitrarily set A0 to 1/8. Okay, at this point, you should see a pattern forming where when we set n equals 2, mu always ended up equal to, or whatever the value of n was, that we started the process with. That's what mu was. Okay. Now, well, going back on any one of these, we have a series again where we have y is equal to z to various powers and so forth for an infinite series. So we're adding up all of these terms. What I did was I calculated the different values of y given different values of z. And that's all this table is. So I'm running z from 0 on up to, and in this case I went up to about 2.3 in increments of 0.05, and calculated the value of y, which would be, in this case, j0 of z. And these are the values. At that point then, on this first series though, on j0, what I did was I used 7 different terms, or I took the series out to 7 terms. So this isn't too far off in accuracy, up to about 4 or 5 significant digits. Compared it to some tables and some books, and it seems to match with some of the printed tables I found. Then I did it for n equals 1, in this case j1 of z, and again calculated what y would be equal in each of those cases. The difference is what I did in these 5 is that I only did 3 terms. It starts getting complicated, but I just chose to use 3 terms in my calculation, whereas for this one I chose 7 terms. But there's no reason you can't go out for a whole lot more terms. Anyway, that's what this whole chart is. Let's see. So now I can plot all this wonderful stuff. And again, I ran my numbers out to a value of z from 0 to 2.5. And now I don't have a copy of this in what I handed out. So sorry about that. And the different values of y are on the y-axis here, going from 0 to 1. And so I plotted the values in the chart for n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and so on. Now, if I'd taken this out much past 2.5, what happens is each of these become oscillations around the x-axis. And even though I didn't plot this one, I stole this off the internet, where they calculated out to a position of 10. And you'll see the same thing. You have n equals 0 starting at 1, whereas n equals 1, 2, 3, and so on all start at 0 and then begin oscillating. Whereas n equals 5 is pretty low and has a very long period. N equals 0 has relatively short periods compared to some of the others. Okay, now to at least show where I got this so that I don't do any copyright law problems. Here's the advertisement. I got this from Math World, and I imagine just about everybody's seen it, but if you haven't, that's it. So there's a plug for Math World. Go visit it and spend money on there or something. But anyway, that's where the chart came from. Okay, let me look at this again. One of the things you want to try and find out is what the zeros are. In other words, where the value of y as it crosses the x-axis, what the values are for j0 at this point, this point, this point, so on. Or if j equals 1 at this point, and so forth. So one thing is to solve these fun equations and find the zeros. So there's various numerical methods involved that are shown. Let's see. In this handout. Okay, let's back up a little bit and talk briefly about a series. It says an alternating function of x real has zeros at intervals, and they may not be equal. In other words, the periods might be getting larger or smaller depending on how it goes. Not everything's like a sine function or cosine function. But since it does oscillate, we can find the values where it crosses the axis. And so this book goes into a couple of ways, numerical methods of how to find those values. The first thing it does is it takes just the first three terms. Okay, so we have a series. And in this case, we're going to use n equals 0. So we had this series. And what they're going to do is look at just the first three terms. And by doing that, they can solve for z and find that it's approximately 2.828. And because they only use three terms, it's an approximation because they obviously haven't solved for the entire series. But it's not a bad approximation using the first three. Next thing they did was they said, okay, now we'll try it by adding in the next term, or the z to the 6th power. And by substituting z squared over 4 and substituting y in there, they get this equation. So all this is the first four terms with y substituted back in this mode. And then as a cubic equation, they could solve for the values of y where it equals 0. And they went through this process and found that y had to be equal to 1.4309, or the first value. And if y was equal to that, then we go back and looking at what z would be when y was that value. And we find that we have a plus or minus because we're taking a square root. Okay. So now we've zeroed in a little closer on the first value where the J0 curve crosses the x-axis. Okay. can go into more numerical methods on how to, in this case, they're employing the Taylor's theorem, Taylor series, and they're going to interpolate between a couple of positions. In this case, they've found two values that are close by at y equals 1.4 and y equals 1.5, found the value of j, and then interpolated to get closer in. Now, all of this is a nice way of going about it, but back when this book was written 40 plus years ago, computers weren't all that available. I imagine these days, the first thing I would have done, now that I'm getting a little more comfortable with Maple, is put it in and said solve. And avoid a lot of that handwritten stuff. Okay. Now, a second thing that's going to happen, going back on the differential equation was second-order differential equation, which meant there's two solutions. And you go through a couple of these pages, and we end up with this solution. Where we've spent most of our time paying attention to the J solution, which is called the first kind, the solution of the first kind. But then I just skipped over a couple of pages that go into the process of calculating the solution by0. Okay, and partly why I skipped through it is when we get done with this, we're going to end up, and I'm going to take a little step here and say something I'm not absolutely sure of, but I believe in most of the cases we're going to end up canceling this term anyway. Okay, and here's a part of the reason. Now we're looking at just the values of j when n is 0 and y when n is 0, and we plotted them. So if you recall, we had an oscillation just like this for j, which oscillated around the 0 axis. What happens with y when we get near y equals, or when we get near z equals 0, as y heads to infinity. Okay, so we end up, I believe, in probably most of the solutions we're going to work with, that you'll find that that ends up being a non-solution for the problem. And so when you're using this, you'll end up having to set b equals to 0. And so that whole term becomes useless to us. So I didn't spend much any time on how it was developed, because I believe for most of our problems, it goes to 0. All right, now going to try a little bit of an application, which I didn't get all the way through, but most of the way. Good old Bernoulli. He was playing around with an oscillating uniform rope hanging from a point, a vertical point. Okay, so we're going to pay attention to this diagram right here and say the displacement from vertical is psi, and x is going from the free end up, and the total length is going to be L, and it'll be fastened in a simple mode at the top. The tension in the rope in this at point P would be T, and that can be broken up into components of T1, which would be a vertical component, and T2 is a horizontal component. And the angle or the slope of T at that position can be shown something, or not the angle, but the ratio of the tensions would be relative to the slope at that point. So we have the tension, the horizontal tension divided by the vertical tension is equal to the partial of xi divided by the partial of x, which is essentially the slope at that point. Doing a little rearranging, moving T1 to one side and differentiating with respect to x, you get this version, or gone to that position. Now, T1 in this case, looking back at this, T1 being the horizontal component at this, excuse me, the vertical component can be equated to the length of the rope times that the mass per unit length times the length up to that point. So it'll be the mass times x. So we can replace T1 with the mass per unit length times x All right, so now we still have the horizontal tension, but it's now set in terms of the mass and the length up to that point. Now, one of the things is that at that point we can look at is the acceleration due to that mass. And so the elemental, let me back up and say the elemental mass at that condition, even though it's at an angle, we can say that the length at that point, I do that very well, partial of s can be shown to be pretty close to and similar to partial of x. Okay, so we're going to say that the mass, the elemental mass is m times partial x. And that here, as it says, equating the restoring force and the acceleration forces, this being the acceleration, the mass times x times the second derivative of the position. So that's the same as acceleration because that's partial to t. Okay, now dividing both sides by mass, moving things around a little bit, we get it in this form. Okay. And again, we did that dividing by mass and g and partial of x. right. The function of psi is going to be a function of x and of t. So we'll set it as a function of x and a function of t. And each of those functions have to be twice differentiatable because we're going to do that in both places. So the function that you choose has to be able to be differentiated twice. Okay, then they do where they substitute psi in there and then divide through by fh. And what this does is get everything on the left-hand side independent of t. Everything over here is dependent on the displacement, or x. And everything on the right side is dependent on t and is not dependent on x, or it's independent of x. Okay, now we're going to introduce in between and say, well, if they're equal to each other, we can also set them equal to any constant. And we're going to pick minus k squared. So we're going to set the right-hand side equal to minus k squared. And then when we rearrange it, and substitute this value, or we're going to substitute omega squared for gk squared. Now we have the equation in this form, which is a typical second-order differential equation, homogeneous, and can be solved in this manner. Okay. Now we're going to look at the left-hand side. And again, do some rearranging of dividing, or should I say multiplying by f over x. And we get the equation in this form, which is now similar to the Bessel forms that we've been seeing, which is the second differential plus 1 over x times the first differential plus the original form with a coefficient. Okay, and at this point, that's what it looks like right there. And as it says, a complete solution to this portion is right here for for n equals 0. And again, we'll probably find that y becomes infinite in certain cases, so we'll end up having to set b equal to 0. And that's what happens in this first step. Okay, that we're going to say, or one of the boundary conditions is that up at the top where x equals L, we're going to replace that with y equals the square root of L. At that point, it's also fastened, so psi has to be equal to 0. There can't be any horizontal displacement at that point, again, because it's fastened at the top. And that'll be true for all t, any t greater than 0. Okay. At the free end, where x equals 0, down at the bottom, again, this is where we said y squared equals 0. By looking at this solution, or the solution portion y0, going back to that chart, if you remember the let's see if I can find it real fast. Remembering this, where it said before that y when this component of the solution goes to 0 when y is, or it goes to unbounded infinity when y equals 0. So if we bring that in at this point and say that y has to be equal 0 at this condition, then since this is infinity, or negative infinity, then b has to be 0. So we drop it back to function is in this condition. All right. Boundary condition at psi equals 0, and this was at the top. Remember what we said at the point of suspension where it's fastened at the top, x equals L and y equals L square root. Psi is equal to 0. There's no horizontal displacement. And that's this boundary condition. So if there's no horizontal displacement, then the function has to be equal to 0. So we set f equals to 0, and so the a is going to cancel, and we're left with j0 2k L square root. And again, remember that L square root right here, where y is equal to square root of x, or square root of L. All right, and that was just placed in this position, square root of L, for that boundary condition. Right here. So what we're doing now is finding the zeros of where the j function crosses the line. And since we already know that that first value is going to be about 2.4, somewhere around there, once we find the solutions for it, let's see. Let me back up and make a substitution. This, remembering that the k value back here, we arbitrarily set k squared times g is equal to omega squared. So let's put that back in down here. Say that k is equal to omega over the square root of g. So when we make this substitution for k, we'll get 2 times omega over, or times L divided by g, both to the square root. And they call that the frequency equation. Okay. So what we'll have is a series of zeros that make this, or give us solution for this equation at this point. And so we would say that the portion inside, 2 omega L over G to the square root, would be the frequency for each of those zeros. And the first zero is 2.405. And so that would be the frequency, again, the first natural frequency. And after finding that value, we can set W1 over 2.4 would be the same as the G over L square root over 2 would be put in right here to find the next one. So that would, this is the second zero, the value at J02, and so forth. So at that point we find the natural frequencies, and there's an infinite number of natural frequencies. An interesting thing in here is that this process, it's independent of the mass. So it's just the length that makes any difference, gravity and the length. So the natural frequency is based on the length, not the mass of the rope. Now, adding all the components back into the original equation, we still have a coefficient A, coefficient of B, and so forth. We put them back together, and we use the initial conditions to solve for those coefficients. At this point, unfortunately, I hadn't gone past that, so I can't make any comments at this stage. So that's about it for me for this subject. Okay.
I would like to continue my presentation about the Bessel function, and I was asked to present the first and the second solutions of Bessel function. The equation we supposed to solve is has a form of this form. And it was solved using the power series which has a form of y equal z in power mu multiplied by the series which has a form of a0 plus a1z plus a2 z in power 2 and so on, where mu and a are the coefficients which are to be determined. So this series we're going to substitute into the equation 1, which has a form of y second derivative plus 1 over z, the first derivative, plus y equals 0. And all these three series we substitute into this equation, and we obtain the following: y is equal to the initial series, and I'm not gonna rewrite it, but the second, so the first derivative will have a form of z in power mu a0 mu multiplied by z in power minus 2 plus a1 multiplied by the mu plus 1 multiplied by z into the power minus 1 plus a2 mu plus 2 plus a3 multiplied by mu plus 3 plus and so on. The second derivative will be
How did you get z minus 2? You have 1 equals z in power mu, etc. Suddenly z in power minus 2 comes out.
Probably it's going to come from the second derivative of the initial series, this one, which I didn't perform by myself, but I rely on the author of the book, which I was reading.
Students, we are asking you, so you must be able to answer the question. Because when you do derivative, I don't understand how you got, z minus 2.
I guess we will have to leave this for the next class, so I will do this at home, and then I'll be able to explain why we have minus 2.
The only thing is that this expression, which is y prime, has here in the book 1 over z y prime. And instead of in front of y prime, it says 1 over z. Yes, just
Well.
the y prime, you see y prime?
This one?
The 1 over z.
Yes.
This means it.
This one, that's the way it's supposed to be.
Yeah, but then you have to still check next time.
So, and the second derivative will be the form of z in power mu a0 mu minus 1 mu z in power minus 2 plus a1 mu multiplied by mu plus 1 plus a2.
We don't see.
Sorry. a2 multiplied by the mu plus 1, mu plus 2 plus a3 multiplied by the mu plus 2 and the mu plus 3 multiplied by z, and so on. So by the definition, when the sum of the three series is vanish, it means the sum of the coefficients of the same powers of z will vanish also. So now we can equate our coefficients to the 0, and we obtain the following coefficients. It's a0 mu in square equals to 0, a1 mu plus 1 in square equals to 0, and then a0 plus a2 mu plus 2 in square equals 0, a1 plus a3 mu plus 3 in square equals to 0. In the first case, we can say that a0 equals 0 or mu equals to 0, which we're gonna leave for the next explanation. But now we're gonna take a look on the second equation, from which we can obtain that a1 equals 0 and mu equals minus 1. And then by substituting this a1 equals 0 into the following equation, we can obtain that a3 is equal 0, and so on. We can obtain that a1 equal a3 equal a5, a7, and so on, equal from the second equation, we can get that a2 equals minus a0 divided by mu plus 2 in square. Also, we can obtain the following coefficients as a4 will be equal to mu plus 2 in square plus multiplied by the mu plus 4 in square, and so in a6 will be the same, except it's going to be the minus sign. And then substituting these coefficients into the series, which has a form of equals z in power mu multiplied by a0 plus a1 z plus a2 z in square, and so on. We can obtain the following equation, which has a form of a0 z in power mu multiplied by 1 minus z in power 2 mu plus 2 in square plus z in power 4 mu plus 2 in square multiplied by the mu plus 4, and so on. So now we can change y for y1, it's just for the explanation purpose, and put before the equality sign. From the
We can use a blackboard.
It's not so much left.
Yeah, for me.
I mean, for me to say.
Let's go.
So from before we know that a0 should equal 1, or mu should equal 0. Sorry. So we suppose that
0 equals 0.
yes.
Then y1 is 0.
Yeah, from this one. So we have the following form for y1, which is equal to
So then a0 equals 1 or 0? Later we have
yeah,
A0
we assume that, sorry,
black.
yeah,
If you would write on the blackboard, you would see that. Paper.
so we have equation for y1, which is equal to z in power 2 over 2 plus z in power 4 over 2 in power 2 by 4 in power 2 minus z in power 6 2 in power 2 by 4 in power 2 by 6 in power 2, and so on, which can be rewritten in the form of y1 equal j0 function of z.
Don't write down.
This one? Okay. So we have the summation sign for the r equals 0 to the infinity, minus 1 in power r, 1 over 2, z in power 2r by r factorial in power 2. From this one, we can make some conclusions that the denominator will go to the infinity, I would say, faster than the nominator, so the whole function is convergent. Okay. And the second conclusion that we can make is that substituting the negative or positive z, we'll have the same same answer. So we can say that the function j0 is a even function.
Okay.
So this one has a definition of the Bessel function of the first kind.
Okay, thank you.
You're welcome.
I'm not going to take anything. So let us do an exercise that I'm doing usually in undergraduate classes. Can you get a sheet of paper and write in the first, get one sheet of paper and write down J. Andres and write just your grade, how much you give to this lecturer from 1 to 10. And then second is A, B, second lecturer. That is the first lecturer, second lecturer, from 1 to 10. And I just want to see what students say. I would like you to prepare better, both of you. Why? Because first lecturer also, I wanted to sleep in both lectures. I, as a student, wanted to sleep. It should be a bit more exciting. It should be. And naturally, lecturer should check before he